All right, so now I want to talk about the relationship between free energy and the equilibrium constant K. They're really two ways of talking about the same thing, and I alluded to this in previous lectures. But the standard free energy change for a reaction, so the delta G of a reaction, delta G naught of a reaction is related to the equilibrium constant K. There's an equation that is very useful that interrelates them through a couple of constants. Negative delta G naught is equal, delta G naught is equal to negative RT times the natural log of the equilibrium constant. You can rearrange this equation if you want to solve for K. So K is going to be, that's natural log, so it's base E. K is going to be equal to E to the minus delta G naught over RT. Now, R is the gas constant, of course, and what you want to do is use the version of it that has units of joules. So you want to use 8.314 joules per mole Kelvin. You want to make sure if you plug things into this equation that the temperature is always in kelvins so that it cancels out the units of the gas constant. K is, of course, a unitless quantity. And when you use this R, you get your delta G in units of joules. So this allows you to interconvert between the free energy change of a reaction and its equilibrium constant. And looking at how they're related, it should be pretty apparent that if you have a nice big K, because of this negative sign, you're going to have a negative delta G. So remember back in the equilibrium chapters, we talked about how a large positive K, or a large K that's a lot greater than 1 rather, not positive, K is never negative, right? So a large K is going to be a driving force towards the products, right? You're going to have more products than reactants. If you have a large K, you are also going to have a negative delta G. So a spontaneous reaction is, in equilibrium terms, a reaction that favors products. Conversely, if you have a small k, or a k that's less than 1, take the natural log of a number that's less than 1, and it's going to be negative, and the negative of a negative is going to be a positive. So the delta G naught is going to be positive in that case. So you get a non-spontaneous reaction or a reverse spontaneous reaction. We would say that that kind of reaction favors reactants rather than products because K is small, so you have more denominator than numerator, more reactants than products. Now, let's consider the situation where K is equal to 1. What's the natural log of 1? Why, it's 0. So that is the border between spontaneous and non-spontaneous, right? So when K is equal 1, delta G naught equals 0, it's a perfect balance of reactants and products. So you have appreciable quantities of both. So we can also say that while K is related to delta G naught, Q is just K, but not at equilibrium. So you may remember that from chapter 15. Q is related to delta G without the naught. So Q is the reaction quotient. Basically, it's like K, but with non-equilibrium concentrations. Okay, so just to remind you, Q is like K, but with usually initial concentrations, not equilibrium concentrations. So basically, when you don't have equilibrium concentrations, free energy becomes your driving force towards equilibrium. Okay, so that's a way to think about connecting the idea of Gibbs free energy with equilibrium. That Gibbs free energy is becoming this driving force towards equilibrium. Let's do an example reaction. Let's take silicon hydride which is in equilibrium with solid silicon and hydrogen gas. Now, you could calculate the delta H naught for this reaction. I'm just going to give it to you. 34.3 kilojoules per mole. It's positive, so it's an endothermic reaction. The delta S naught of this reaction is negative 75.6 joules per mole Kelvin. So it's a situation where you can't possibly get a negative delta G. When you plug those into the master equation, you get a delta G naught for the reaction that is 56.8 kilojoules per mole. So that is positive, so this is going to be non-spontaneous or reverse spontaneous. So let's calculate now the K for this reaction. The K for this reaction, now I'm going to give you the equation for that again. K is equal to E raised to the power of negative delta G naught over RT. That's going to be equal to E raised to the power of minus 56,800. I had to convert the delta G to joules. Divided by, now always assume that your temperature is 298 Kelvin unless otherwise specified, joules per mole Kelvin. So I'm going to plug in 298 Kelvin for my denominator. So once you plug all that business into your calculator, you should get a K value around 1.1 times 10 to the minus 10. And it's K, so it's unitless. So this is a teeny, 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 tiny K. Very small K. Let's think about what K means in this case for this reaction, looking at the reaction. Let me zoom out a little bit. So looking at the reaction K, I'm just going to do it based on the partial pressures. The solid doesn't appear in K. Let's just take the partial pressure of hydrogen gas over the partial pressure of SiH4. I'm going to have to square the hydrogen gas because I have a 2 as my stoichiometric coefficient here. That is going to be equal to this teeny tiny number, 1.1 times 10 to the minus 10, approximately equal to this number. So this means that the pressure of SiH4 must be much greater than the pressure of H2 because K is so small. So we must have a much larger denominator. So let's think about this in the context of Q and how we can kind of push this reaction in different directions. Q is equal to the pressure of H2 over the pressure of SiH4 as well, just not at equilibrium. Now, if Q is equal to KEQ, we are at equilibrium. So basically, you have the equilibrium concentrations. When I say KEQ, I mean K. So I don't mean to be confusing there. Hang on, let me get my little eraser to erase the EQ so I don't confuse anybody there. EQ just means equilibrium constant. So if Q equals K, we are at equilibrium. And delta G without the naught is equal to 0. Now, let's imagine what's happening if Q is greater than K. If Q is greater than K, that means that you have excess H2, excess product. So according to Le Chatelier, the reaction is going to proceed in reverse. It's going to be reverse spontaneous. I hope that makes sense, right? So if Q is greater than K, the reaction will proceed in reverse because you have excess H2. We call that reverse spontaneous or non-spontaneous. That means that the delta G, not the delta G naught, but the delta G of the reaction is positive. It's reverse spontaneous. Finally, if Q is less than K, the reaction proceeds in the forward direction because you are going to need to create more products to get close to K. Remember, according to Le Chatelier, you're always trying to reestablish K. When you start with Q, the system is going to go towards making Q into K. So the reaction is going to proceed in the forward direction. It's going to be spontaneous in the forward direction. In that situation, delta G without the naught would be negative. Okay, and again, the driving force is towards equilibrium. So we can combine all of these ideas with one big equation, that delta G not at equilibrium is equal to delta G naught plus RT ln Q. So this equation is meant to be applied to non-equilibrium systems. So this is non-equilibrium delta G. Delta G naught is the equilibrium delta G. Q, of course, is a non-equilibrium term. So when you are not at equilibrium, you have these driving forces towards equilibrium. That's what free energy is. So if you're actually at equilibrium, then Q is equal to K, and this expression reduces to the one that we wrote down before. So at equilibrium, Q is equal to K, and the expression becomes the equation that we started out with. Delta G naught equals minus RT ln K. All right, so I hope that makes sense. And the actual manipulation of this equation is very easy. It involves plugging in numbers. Thank you for listening.